Bowen from NEAR, and today I want to talk about stateless validation and how it solves the scalability problem. So let's start with a problem that maybe many of you here are familiar with, which is the state growth problem, and it's a huge obstacle to blockchain scaling. Basically, the problem is as follows. As a blockchain gets used more and more over time, the state would accrue through usage of transactions, people calling smart contract, more people creating accounts on the blockchain, so on and so forth. If we take Ethereum as an example, I think the state size has been growing at about tens of gigabytes every year. And obviously, this depends on how exactly you count the size of the state, because with Merkleization or with the MPT structure, there comes this overhead with many hashes in between. But anyways, the state is estimated to be several hundred gigabytes today, and it's keep growing. The problem with that is it becomes more and more expensive for people to operate a node, whether that's a validator node or just people want to operate a full node. And at some point, this problem would become so severe that it becomes very difficult for people to keep up with the operation of the network. So what are some of the solutions we have to this problem, since it is not new? Even I think at the beginning of Ethereum, people have been thinking about the future and how they would address this problem. So I think there are generally two directions people are exploring. One is sharding. So basically the idea is that instead of having one global state, we divide the state into many states of smaller shards, and none of the nodes in the network actually need to store the entire state. And the other direction is state pruning. So this is the idea that even though the state itself can be very large, let's say on the order of several hundred gigabytes or even larger, you don't actually need all that state all the time. For example, when you execute a block, there is a gas limit associated with that, and it naturally implies that there is a limited set of state that you can touch during the execution of the block. So what you really need is that you really need the state that's needed for execution of a specific block. So the idea is that can we find some way to store only the state that you need for the execution that you need to do? And this is where the stateless validation idea comes in. The idea was originally proposed by Vitalik back in 2017. And roughly the idea is as follows. Instead of every single node in the network having to maintain the entire state in order to execute and verify the execution, the network's divided into two rows. There is the validators who do not maintain any state locally, and they rely on state witness to execute the blocks. On the other hand, there are block producers who is responsible for producing blocks. Obviously, they maintain the state locally, and they also produce the state witness. So the state witness here is just a glorified word for saying that all the state pieces that are touched during the execution, and also the proof that it indeed belongs to the correct state root. So if a validator receives state witness, then they can verify that the state witness indeed are referring to the state that belongs to the state that's specified by the state root that they know. So this idea is called weak statelessness. Basically, there's still some entity in the network who's maintaining the state, but the vast majority of nodes in the network do not actually need to store the state locally. So the advantage here is that because the validators, or like majority of them, don't need to store any of the state locally, it relieves this huge storage pressure from them. And also it eliminates this downstream problem where the validators don't really need to think about what happens when the state grows large, because they themselves don't need to store any state locally anyways. So for each block, they would receive the state witness required to execute that block, and they just do the execution based on that, and verify whether the execution is accurate or not. So on the other hand, the block producers, they do need to store the state, but roughly the idea is that there only need to be a few of them in their entire network, and because of this, they can afford to operate more expensive hardware and potentially get more reward as a result. So this asymmetry of rows may feel strange at the very beginning, but it's actually a very elegant design to reduce the overhead of the network and improve decentralization. So this idea is roughly that a small portion of the network need to operate more expensive hardware, but at the same time, they're not gaining disproportionate power to control the network. So the block producers here, yes, they do run more expensive hardware, they do more stuff, like not just producing the blocks, but also producing the state witness and distributing the state witness. But there's not much they can do more than what they can already do today. For example, they can decide what transactions they want to include, they can decide what transactions not to include. But beyond that, there's no way for them to crop the network by themselves because the validators would actually validate all the execution and the state witness as well, verifying that they actually belongs to the correct state. Also, the execution is also verified by running the blocks through the state witness provided by the block producers. So on the other hand, validators themselves are pretty cheap to operate, and because of that, there could be a lot of them, and that's definitely beneficial for the decentralization of the network. Now, I would argue that this is great, but it's not a full solution for the scaling problem. So the main problem here is that while this introduction of this asymmetry of rows greatly reduces the pressure, the hardware pressure on most of the nodes in the network, we still cannot just simply ignore the block producers. So basically, the state growth problem still exists for them. And if we don't deal with this problem, it means that at some point, let's say the state size reach on the order of several terabytes, it will still become difficult for block producers to actually store them and operate them, because it's not just about storage, they also need to be retrieved in a relatively fast way when you actually execute a block. And the failure to do so may cause degradation of the performance of the network. And also, just to actually operate those block producers, it should not be so prohibitively expensive that only 1 or 2 people are able to do it. Still, there should be a handful of those block producers. Otherwise, the network can easily suffer from a liveness failure if those block producers go offline. And that's not what we want. So what solutions do we have to address this problem? In one of the earlier slides, I talked about sharding. To reiterate, this is basically the idea that the global state can be divided into shard states so that no validator needs to maintain the state of all the shards, meaning that they don't need to store them locally, and that the networks generally scales with the number of shards. Obviously, there's overhead associated with the scaling. For example, the network needs to coordinate which validators get assigned which shard and how the cross-shard communication actually works. But in general, it scales with the number of shards in the network. So the idea is that we can combine those 2 different approaches together and produce an elegant design that would solve the scaling problem for L1 blockchains. So roughly the idea is as follows. We still have 2 rows in the network. There's the chunk producers, so that means the shard block producers, and the validators. So the chunk producers would be responsible for producing chunks or shard blocks for each shard, and also the state witness associated with those chunks. So the validators, they do not actually need to maintain any state locally in order to do the execution. And the validators, on the other hand, would get rotated on every single block into validating the different shards. As we'll see, this is for security reasons. So in a lot of the earlier designs for sharding, the security assumption is big problems because with the more shards that you have, there's this problem that cannot be ignored, that it's possible for some shards to get corrupted even though the global assumption, the global BFT assumption of no more than 1/3 malicious validators may still hold, meaning that there could be the case that globally there's only 1/3 of validators, but this assignment to shard means that some validators, some shards get a lot of malicious validators. And there's also this adaptive corruption problem, which is that even though the assignment may be fine, but over time, the validators of a single shard can get corrupted, and they would conspire to produce something like an invalid state transition and can mint a lot of token out of thin air, and that's definitely not great. So in the stateless validation design, because the validators actually rotate on every single block, and the assignment to shards are dictated by the randomness beacon provided by the protocol, and it's not possible to bias that. There's a security assumption, obviously, depending on the system parameter, but basically we can make it such that the probability of some shard getting corrupted is extremely low and won't happen in our lifetime. So that is kind of what it makes it secure and avoid the need to having to design this fraud proof, which is very difficult to implement and also to test. So that's not the only benefit. Obviously, as we kind of already talked about regarding stateless validation, the network is more decentralized over time, and because the validators, they don't need to operate expensive hardware, they don't need to store any of the state locally, and the network become more decentralized because of the lower cost of operating a validator. And there's also an interesting benefit as a result of this design change, which is that we can actually try to hold the entire state in memory for execution. So let's say because of this sharding design, we can have many shards in the network, and as a result, it's possible to limit the state, the size of the state for each shard to something, let's say, 50 gigabytes. And for a chunk producer, they can actually operate a somewhat expensive machine, let's say a machine with 64 gigabytes of RAM, which is actually not that expensive today, and actually hold the entire state in memory during the execution. And on the other hand, the validators themselves, when they receive the state witness and do the execution, the state is naturally held in memory. So basically, during the entire execution on different type of validators, the state is always being held in memory, which means we can decrease the gas cost for storage-related operations and make the throughput much faster. So this is also a very future-facing design, because today in this design, the chunk producers would generate state witness, and then they disseminate that to the validators. The validators would verify them, would verify the chunk execution using the state witness. But there is this obviously non-negligible overhead created by communicating the state witness to the validators, and also validator having essentially to do the same execution as the chunk producers. With zero-knowledge proofs, we can actually replace that. For example, the chunk producers, instead of generating state witness, they can generate a zero-knowledge proof, which is much, much, much smaller, on the order of several hundred bytes or several kilobytes. And those zero-knowledge proofs are communicated to the validators. The validators, on the other hand, would verify the zero-knowledge proof, which is also much cheaper than doing a verification of chunk execution today. So this is overall would make the system even more decentralized and even more scalable, because it's going to be way cheaper to operate a validator under this assumption. So this design that I just talked about, we already implemented, already almost done with implementation at Near. So if you're familiar with Near, you probably know that we had this nice sharding design back in 2019, and we recently updated the design to include the stateless validation change, and we're currently running a incentivized testnet. So if you're interested in learn more about that, you can find it at near.org/stakewars. And also you can scan this QR code if you want to learn more about the technical details of the design. So this would link to the updated white paper that talks about all the details of how it works on a much deeper level. And we're aiming to launch mainnet at the end of Q2, and hopefully that would bring a lot more scalability, transaction throughput to the network. And yeah, that's it for my talk. Thanks.